this video, we are going to see about frequency shift keying, which is also called as FSK. In FSK, commonly we are talking about binary FSK. And there are also a format called multiple frequency shift keying. But commonly we are referring binary frequency shift keying. Binary frequency shift keying means only two different frequencies are used. For example, if data pulse 0101 is transferring, then there will be a carrier frequency and two different frequencies near the carrier frequency. For example, if the carrier frequency is 100 Hertz, then maybe one is represented by 900 Hertz and other one is represented by 1100 Hertz. So, two different frequencies which is near the carrier frequency represented by two binary values. And when compared to amplitude shift keying, it is less susceptible to error. That means it is less capable to being offense by error. And it is commonly used in high frequency radio transmissions as well as in high frequencies on coaxial cables. Okay, let's see about binary frequency shift keying. As I have already mentioned, in binary frequency shift keying, the two binary values, that means 0 and 1, will be represented by two different frequencies. That is F1 and F2, which is equal and opposite amount from the carrier frequency FC. If FC is 1000 Hertz, F1 will be 900 Hertz and F2 will be 1100 Hertz. Or F1 will be 800 Hertz and F2 will be 1200 Hertz. It is differ in equal and opposite amount from the carrier frequency. That is important. So in BFSK, binary one is resulting in the waveform of A cos 2 pi F1t, and binary 0 is represented by 2 pi F2t. But in ASK, it is represented by A cos 2 pi FCT for binary 1, and binary 0, it is represented by 0. Here, frequency is carrier frequency because we are modulated with carrier frequency. And for the zeros, we are not giving the carrier frequency. But in the binary frequency shift keying, it is modulated with equal and opposite amount of frequency from the carrier frequency. So here 0, 0 is represented by one waveform and 1 is represented by two waveforms here. Here you can see similar pattern is maintained for every ones, and for zeros another similar pattern is maintained. if you see BFSK here, as we have already seen what is baud rate and what is bit rate. Bit rate is how many bits are transferred in 1 second. That is BPS. And baud rate is how many signals are transferred in 1 second. Here, in BFSK, 1 bit is represented by one kind of waveform. So, here it is 1 baud. And here another represented by another waveform. So, here this is another baud. So, here 1 bit is represented by 1 baud. So, here bit rate is equal to the baud rate. If we take it's 1 second, 5 bits are transmitted and 5 bauds are transmitted. As we have already seen in the previous videos for the digital data into digital signal, here was in some cases 1 bit is represented by the 2 bauds. That means 2 different signals. But in this case, it is represented by only 1 waveform. So, bit rate is equal to baud rate. And when we see about the multiple frequency shift keying, here from the word itself we can get to know more than 2 frequencies are used. In BFSK only 2 frequencies are used, but in MFSK more than 2 frequencies are used. When using more than 2 frequencies, we can represent more than 1 bit at a time. Because normally digital data is zeros and ones. So only 2 frequencies are enough to represent zeros and ones. So if we are using more than 2 frequencies, for the one kind of frequency, we can able to represent more than 1 bit. So when representing one signal element by using more than 1 bit, then it will be bandwidth efficient. When we are seeing about the digital data converting into the digital signal, I have mentioned that point. That is, when the signal rate increases, host will be increases. So, when one signal representing more than 1 bit, host needed also get reduced. And with the same signal rate, we can able to transmit more data. So it is bandwidth efficient. And when compared to BFSK, it is more susceptible to error, because as we already know, when we represent by more than two frequencies, for example, one wave is transmitted in BFSK, that is 900 Hz and 1100 Hz. But here we are using four different frequencies, that is 700 Hz, 900 Hz, 1100 Hz and 1300 Hz. If one waveform is getting error and it becomes 800 Hz, then it will be difficult to find in MFSK. It is representing 900 Hz or 700 Hz. So the chance to be getting error is high in MFSK when compared to BFSK. And I have already mentioned the point. Each signaling element represents more than one bit. Here, the transmitted MFSK is represented by the form A cos 2 pi Fi t. In BFSK, we have simply write A cos 2 pi F1 t for binary 1 and A cos 2 pi F2 t for binary zeros. But here, according to the number of different signal elements, we are using this format. Here, Fi is equal to this one. Fc means higher frequency. 2i. I means which frequency number we are referring. And M means number of signal elements. For example, if we represent one signal with 2 bits, then 4 different combinations are possible. 0, 0, 0, 1, 1, 0, 1, 1. So here we have 4 different signal elements to show these 4 different combinations. So this M means number of different signal elements. And FD means difference frequency. And it denotes the difference this is difference frequency. And this number of different signal elements, M is equal to 2 to the power of L. For example, as I mentioned, if one signal is represented by 2 bits, that bit is L. Then 2 to the power of 2, 4 different combinations possible. If one bit is represented by, one signal is represented by 3 bits, then 2 to the power of 3, 8 different signal elements are possible.